Hi, I'm going to talk about a project or a problem that I ran across for oversized aggregate correction on a levee or a berm. It was basically a dirt dam that was damming up a river or a stream. And it was my task to use a Troxler 3430 gauge to determine if the workers were having good density and good water content in the lifts. You need the water in the lifts for the hydrogen bond network to hold the dirt together, and you need the compaction also to hold the dirt together. So my task was to test both the density and the water content. When you go to construction site, you see them trucks with the big old rollers that go over the subgrade. Well, that's what they had. Plus, they had trucks with the same tank in the back that was wetting the whole uh, lift so that you had the optimal moisture versus density as it went per lift. It was about 40 lifts up, about 40 feet more or less up in the air. So it was my task to test the levee, dry density, and optimal moisture content. The problem was that there was 5-pound boulders. Those little boulders are large cobbles thrown out throughout the berm, and they were not accounted for in the Proctor set. So I had to take this treatment using AASHTO T99 for oversized aggregate, and I corrected for OM. Like I said, we're having good density, so I didn't bother with that. But I should have at least looked into what the density offset is because of the following. Okay, these are the curves, your density curves. Density, which is compaction, versus moisture content, which is down here. Your X is your water and your Y is your density. So you get curves that look like this, little hill tops or parabolas, if you will. And so, hold on a minute. Okay, here's the data set. Slope tangent to the curve has a name. It's called the zero void volume. Basically, it's mathematical treatment of this data set by differentials from the guys that made the PDF, the engineers. We just get the arithmetic on field and we go about just plugging in the variables based on the empirical results that are given from the data set and from the Troxler gauge readings and plus from the lab work. Okay, so what happened was the the density was great. We're getting like very good density readings. The moisture content was off by quite a bit, and they were off by quite a bit all the time. Even though these guys were doing a good job, there was a like the tolerance values about what the OM should be was off by far to the point of failing them. But because they're doing good work. Is just that the Proctor set was wrong from the lab because they didn't account for the 5-pound large boulder in a bucket. The buckets are them Home Depot buckets. They're about 5 gallons, and they're from Home Depot. And you get a 5-pound rock and you put it in there. You're supposed to replace the 5-pound rock in the lab with appropriate fines so that the accompanying soil that's there is affected so that the OM and the density is affected too. Okay? This is a theoretical treatment of compaction versus OM that takes into account the empirical value of what a 5-pound boulder would be in OM and in density. Okay? Okay, so to scale density versus moisture, here's the same curve, but it's to scale. I just thought I'd put it up here. That's what the lab guys do to go about their work, which they do good work. It's just that the Proctor was incorrect. They didn't take into account the appropriate geographical survey that should reflect what the geographical survey is in a bucket. It's very difficult to do that every now and then. So ain't nobody to blame. It's just that the dozer don't really care if there's a 5-pound boulder under it or not. Okay, and that 5 pound little boulder should have been put in the bucket. Unfortunately, it wasn't. Okay, so the AASHTO T99 oversized aggregate correction says Annex A, that's where it's at. Some of these PDFs are different numbering system for this particular oversized aggregate uh, situation, right? It says that it can't pass a 19 millimeter sieve, which is about an inch. It's a pretty big old little cobble, about the size of a regular rock that you use to throw at a dog or something, knocking down your trash can or something. It's just a regular rock. 19 millimeters is about the diameter of that rock. And so these were 5 pound. They're huge. They're big old rocks thrown all over the side of the berm, right? And they're run over by the dozer. So I figured, and there was about 30% large aggregate when I asked the QA about just looking at how many rocks were out there. There were big old rocks. I said, it's about 30%. What do you think? He says, yeah, it looks like it's about 30%, dude. And they just weren't accounted for. Okay, so here's the treatment. Annex A and AASHTO T99 for oversized aggregate. Here's the mathematics, simple arithmetic, telling you how to go about doing it. All right. It says right here that there's, let me see, I can barely see it. Hold on a minute. It's basically 30 to 70, so it's about 30% large aggregate versus 70% fines. Okay, so here's the arithmetic with the definitions of what these variables are. It's very simple to find. Just read it. It tells you what they are, and they're given to you from the Proctor set in the lab work and what your dropper gauge says. Okay, application. Here's the optimal moisture correction equation. Okay, and using what your original data set was plus the 5 pound boulder or whatever weight you would suspect would be at whatever. If it's about 30% is what the variable would be based on what your QA says. 2.1% is the amount of water content in the rock. Okay, so here's the density. Now don't forget the density. Because we're getting great densities, I didn't do the density, but I should have done the density. Okay. End notes. Proctor set is a geographical survey. Proctor bags and buckets are about 5 gallons or smaller. Include a 5 pound small boulder if there is one out there. Whatever big old rock that's fairly big that you don't want to put in that little bucket, put in there anyway. If it makes up 30% of the land topography. Moisture content of a rock is given empirically in this publication. It's 2.1% water content in a rock. Add this to the original optimal moisture content that you're getting on the field, and you get the OM correction offset is thus justified on this treatment of data. It's not random. Random is that you get the number that's failing and you jack it up a little bit so it passes anyway, which is unethical. You got to do this at least, because it's ideal to run the whole thing all over again, but it takes weeks, and there's them big old dozers and 15 tons of steel up there per rig, and it ain't moving, and it costs money to have it there, and they're going to get angry at you. So try to do it as quickly as you can. Now, if you're gifted enough to go about doing this work in a weekend, all right, more power to you. But this is a way to do it empirically from the theoretical treatment and the previous data set. End of presentation.